Good afternoon, everyone. I intend to split this afternoon's work into three sessions. The first session will be an introduction to the theory and operation of cache memory. The second part of the session, the second session will be the rise of digital machines, and in this part we will look at the actual design and implementation of machines. And finally, in part three, we shall study more Python, and in particular we're going to focus on while loops, the conditional statements, and a couple of other quite important elements. I have three notices. First of all is that I can make several ebooks on Python available, if not the references. And it's very much up to you which book you choose. I mean, it's a good idea if you actually have a look at some of these books and decide for yourselves which you find the most helpful. The second notice is a slight advance warning of the fact that I will be setting some written coursework soon after topic 5. In general, I'll give you references for most of the work covered in this course. The recommended book at the beginning of the module, which you can inspect, is very good for gaining a solid background in the area. Okay, so we'll make a start. The locality principle. This is what the first part of today's session is all about. Locality of reference is a fundamental principle of computing with many applications. So we're going to talk about the locality principle, and it has two forms, which I'll explain to you. I'll give you a formal statement of the two principles, and I shall give examples, both from practical life and examples from computing. So last night I actually heard a government advisor talk about the coronavirus distribution, and I thought I'd sort of cite this as an example of an application of the principle of locality, so it might surprise you a little bit. So one of the government advisors explained an alleged way in which the virus is transmitted. It's this: people that tend to visit hospitality sites, for example restaurants and cafes and so on, tend to be quite social people and will in all probability visit another hospitality centre within a week. Hence, if one of those people has the virus and visits such a centre, mainly on account of the closeness of contact that that person will have with others, and secondly, the closed air environment, there's a strong likelihood that as many as n different people will be infected after a week, and so the virus will spread. You might think this is a bit of an odd introduction, but as you'll come to see, the principle of locality is at issue at some point. What I want to talk about is the virtual collapse of the classical memory hierarchy. And to introduce all this, you will have to realise that computer memory comes in all shapes and sizes. And in fact, it appears as a hierarchy, in fact, a pyramid with different levels. At the top of the hierarchy, at the top level, at the tip of the pyramid, you find very, very fast memory, which is characterised by the fact that it can't hold very much data. It's small capacity, has small capacity. It's also very expensive, and it's very, very fast to read from that memory or to write data to that memory, i.e. At a lower level, the memory has a bit more capacity. It's a little bit less expensive, and it's quite fast. Not as fast as the memory found at the top of the hierarchy, but pretty fast. And so you go down the levels of the hierarchy until you come to the bottom, where you find memory comes in virtually unlimited amounts of capacity, is incredibly slow, not very useful, but it's still memory. You can still store data on the particular medium I'm talking about. And moreover, it's incredibly cheap. Why? Well, it's this memory at the bottom of the hierarchy is of the form paper tape, and you can encode data on strips of paper or reels of data very easily. Unfortunately, to get the data on and off the paper in the form of perforations in the paper takes a long time. So here we go. I think I've introduced the hierarchy reasonably well, and I'm going to use what follows to introduce you to several important topics. And from last week we realised that computer systems rely on fetch decode cycle for computation to take place. And in what follows, I don't always fully explain the terms I use, but at some point these terms will be explained and you will become comfortable with them. And we all know that storage media, as I've tried to outline a moment ago, varies enormously with respect to speed, cost and storage capacity. For example, there exist very fast memories, but typically they can only store small amounts of data. And recently we studied hard disk drive storage and compared this briefly with solid state device storage, which is more expensive but faster, much faster. And as I said, in the old days, like in the 1940s, early 1950s, I think, as a historical matter, perforated paper tape was used and is in principle of unlimited capacity. And what also comes to mind, I suppose, is cloud storage. I mean, perhaps some of you have had experience with ASUS web storage, which is capable of storing 1 or 2 terabytes of your data at a fairly low cost. However, it's pretty slow. If you try and get off a picture, it's going to take a noticeable and appreciable length of time. So the question is, at this point, could we arrange things so that these differences in speed, in other words, access time, in terms of seconds versus nanoseconds, appear to disappear? I mean, the reality is that these access speeds, these access times, in reality aren't going to disappear, but we can make it, we can organise systems in such a way as though they appear to disappear. In other words, we can use any memory that we want to without any kind of penalty. Well, it looks possible, if only on the basis of thinking about the problem for a short time. We can perform a Gedanken experiment, as the Germans would say, a thought experiment. So think about this. If I want to use quite a lot of data which is currently stored on paper tape on Monday, I could arrange for that data to be, first of all, buffered or moved or stored onto a faster medium, i.e. faster memory, over the weekend, so that the data contained is immediately accessible on demand on Monday. It's there, it's ready, I can load it. I don't have to wait 2 days to get the data off, making the system that needs the data wait. I don't have to do that. Certain memories are so expensive there simply isn't the market for it, apart perhaps from the use in special fast registers or very special applications that need speed. And you might want to research memory made from, if you've done any chemistry, from gallium arsenide. Check it out, just find out. Right. The secret in providing a generally effective mechanism for collapsing the traditional hierarchy. What I mean by that is making all memories appear to be the same in terms of access speed, more or less, depends on exploiting the theory of locality, of reference and spatial reference. Right, so I'll try and split that up and analyse the theory of locality into two principles and explain its operation and give you some examples. More specifically, in terms of computer science, there's a specialised application of that theory to what is called program locality. And research indicates that every program that you could possibly write is going to have certain locality properties. And locality is going to be the secret of our being able to treat the hierarchy of memory as though memory's got a uniform access speed across the board. So the technical phrase at the beginning of this section that describes what we intend to do, i.e. the logical collapse of the classical memory hierarchy in respect to memory or storage access, makes a bit of sense in this context. Our attention is going to be focused on memory within a PC or a router or your laptop or whatever. The general principle applies to far more general systems such as internet service providers, wide area networks and local users' PC, and is relevant to virus super spreading too, and I'll try and make sense of that a bit later on. So there's a general principle of locality. It has two forms. Spatial, that's to do with space, and the second is temporal, i.e. to do with time. And the general principle can be couched in probabilistic terms and small periods of time. So here we go. So here's a formal statement of spatial locality, and it says this: if an event Z is taking place in a locality or region L, then there is a relatively high probability that the event Z is also taking place in locality or region L1, where by hypothesis L1 is close to L according to some metric. I mean, the metric could be time or space or other measurable dimensions. All right. So here's a concrete example, and a very down-to-earth example. Let's suppose it's snowing in Bond Street. I mean, Bond Street is a street in the middle of London that runs from west to east. And according to the principle of locality, there is a high probability that it is also snowing in St. Christopher's Place. And St. Christopher's Place is a couple of 100 metres from where I'm actually standing at the International Foundation Group classes. And it's a narrow passageway, relatively narrow passageway, that connects a road onto Bond Street, that connects a particular main road into Bond Street. So it's only a couple of 100 of metres away. So that seems a reasonable conjecture, namely there's a high probability that it's going to be snowing in St Christopher's Place as well at the same time. In programming terms, we only need to think about accessing a data array, which is a list-like structure available to most programming languages. And the array might be given the name myArray, and its elements can be accessed by writing myArray in square brackets 0, myArray square brackets 1, and so on. myArray 0 actually stands for, or represents, the first element of this list-like structure, or this strip of data, if you like. So, if some program P is currently accessing elements 34 to 87 of my array A, I put actually array here, it should be my array A, then the principle of locality says that there's a high probability that region 87 to 88, elements 87 to element 88, will also be accessed in the near future. And here the specific event is an array access by means of specifying an index. And the locality at issue here is the physical or logical locality in which the array is stored on some medium or in some memory. So, for example, typically a programmer can actually store data, and the data will be stored in a particular region, in elements of memory that are next to one another. So, for example, if I access one element of the array, there is a probability or a likelihood that the data element, the next data element stored in the array, is going to be found in the same region of memory, because all the list is going to be stored in what's called a contiguous strip, a contiguous area of main memory. So later today we're going to have a look at loops or while loops in programming languages. What I have in mind here to illustrate locality, principle of locality, in its spatial form is this. Whilst the number I is less than the length of the array, i.e. less than the array bound representing the length of the array, I want to process the ith array element, and then I is going to be incremented by 1. So initially perhaps I is going to be 0, and 0 is less than the length of a particular array. For example, I'm going to process the 0th, in other words the first array element, and then increment I by 1, I get 1 is less than the array bound, process the second array element, and that is array 1, array number, the first location, first position in the array, and so on. So I is going to be incremented to 2, 2 is less than the array bound, and I'm going to process the third element of the array. And what processing the array might mean is simply to add the particular array element to the sum of the last array elements that you've looked at. So I'm just accumulating, I'm forming the sum total of every array element, which I'm assuming are integers. So what this means is that I'm just going through the array element by element and doing something with each element. And as you can see, if I'm going through the array then there's a very high probability that I'm going to actually look at the next array element and do something with it. And locality, the principle of locality says, yeah, that's right. There's a high probability that if you're looking at part of memory, then you'll look at or access the next bit of memory. And here's an example of where this happens. So the other principle sort of locality is temporal locality. And the principle states the following. So I want you to remember this definition, get this word perfect, and come to understand it, what it's actually saying. It says, if an event E takes place at time t1, there is a high probability that the same event will also take place at time t2, where time t2 is close to time 1. So the time intervals are very small between t1 and t2. And a practical and concrete example of this is, it's raining in Bond Street at 1 minute past 1 in the morning, and therefore, according to locality, there's a high probability that it will also be raining at exactly the same place at 5 minutes past 1. So, okay, let's switch context. Let's think about programming. What we find to be the analogue to this is this. If a region of memory has just been accessed, i.e. it's been read, within a program, there's a high probability that exactly the same area of memory needs to be accessed again in the near future. Okay, and all you need to do to understand the relevance of locality is to understand why locality principles hold here. Have a look at this. This is another while loop example, and what it says is, whilst the variable c is less than 200, execute a code block. I mean, it might be a single instruction, or it might be 200 or 300 instructions. So for 200 times, beginning with c equals 0, and incrementing c each time around the while loop, execute the same code, the same program instructions, the same instructions, in other words. And you'll see, if you think about it, the same instructions will be repeatedly executed. And for this to happen, you will understand that on the basis of our understanding of the computer architecture that we obtained last week, whenever an instruction is to be executed, the CPU will look at the program counter register to find the address of the next instruction to be executed. And therefore, the same code will be fetched from memory, same 10 lines of code which constitutes the code block from memory. It'll need to be fetched up to 200 times, and each fetch of an instruction or block of instructions is going to take time. So let's try and make a bit of progress. The point of all this is this. If we have two memories, M1 and M2, which differ in bandwidth, speed of which it operates, and by choosing a memory M, which has a bandwidth close to that of memory 1, we can arrange matters so that differences in bandwidths between M1 and M2 stop mattering, cease to matter. when it comes to allowing access to what's in M2 to M1. So what am I saying here? Well, M1, I'm thinking of it as fast memory. Now it could be a register in the CPU module. It could be, for example, the accumulator. And I want to maybe put data into the accumulator. Maybe I want to do, put the same data in the accumulator because I'm adding, say, 200 numbers together. And I'm just thinking, well, surely, rather than repeatedly fetch the same instruction or instructions from relatively slow memory M2, if I place the instructions that I'm repeatedly fetching into a local high-speed memory, then I can transfer from M, this fast memory, which I call cache memory, into M1 very quickly, very easily. I don't have to wait for slow M2 to be read and for the data output or the instructions output from M2 to have to transport them back all the way back to M1 using the data bus. In other words, if I put what I need to be fetched from main memory into local high-speed memory M, there's going to be a big speed advantage. So the idea is this. I've got slow old main memory here, M2, and I've got something like a CPU register, the fast memory, perhaps in the CPU itself. And I'm going to fetch data or an instruction to M1. It's going to take maybe a journey time of 500 nanoseconds. Okay, you might think, well, that's next to no time, but it's quite a lot of time. What the alternative way of organizing this system is that you've got main memory here. You fetch an instruction or data and you place it into M. This is memory M. This is the fast memory. Its access speed is very close to that of the register. Okay, so concretely, M1 might be a processor register, and M2 might be a memory that's considerably slower. The time taken for instructions or data to be accessed from M2 might take 200 nanoseconds. And it's a long time if your computer is executing instructions or working on data at 4 gigabytes, at the rate of 4 gigabytes per second. Right. M1, unfortunately, would have to wait until the instruction or the data has arisen. So there's nothing worse than making a computer wait for its next instruction. It's ridiculous. It's a waste of processor time. All right. If you find of any of this troubling, think of the case where here's a it's a slight aside, but I'm still reinforcing the idea of the benefits of acknowledging locality. If you find any of this troubling, think of the case you're wanting to read a book because you need to understand a particular bit of science in order to do your homework. So you go to the library, do some work, and return home. And a bit later on, you need to refer to the same book because you realise that you didn't quite understand what you were reading. So you go all the way back to the library. This again takes time, and at the point where you need the book, you will have to spend time travelling to the library every time. So the solution to this awkward problem of spending a lot of time to get what you need is this. You take the book home for immediate access. You keep it at home. There's no travelling by tube and bus to get to the library involved. Not unless the book's a reference book and you're not allowed to take it home. Right. So, a simpler example of the applicability of um, the principle is this. When you sit down to work on, for example, your homework, typically you will collect all the things you need by your side. For example, a laptop, a textbook, your notes, pen and paper, a calculator, and so on. So that you don't waste time by having to go downstairs to get your laptop, bring it up, plug it in, get onto the internet, and you've got the textbook, and you can mark in the textbook the place that you need to read, and you've got your notes in case you need them, and so on. So what's actually going on here is the need to anticipate what you will actually require ahead of the point of the need for something. So, but you're going to be informed by the principle of locality. For example, in the case of computing, if you access a particular piece of data, locality says two things. It says that there's a probability that you're going to access that particular piece of data again in the near future, or you're going to access a bit of memory very close to the area that you've just accessed or read. So if the next block of instructions can be anticipated or predicted from the principle of locality, maybe, and loaded into your high-speed memory M, then when M needs more instructions, these can quickly be loaded into M1 from M. So what we're looking at is this. This looks horrifyingly complicated, but it's not actually. Here I've got a CPU unit. So it's got things like an accumulator and an internal controller and so on. This thick line is the data bus, and it's connected to the memory buffer. I think it's the memory data register. So I've got a little register here. The whole system operates in following. The CPU might issue a read instruction, which, other things being equal, is connected to the main memory. And you can read main memory when the CPU's placed an address in the memory address register. It waits a little bit of time, in fact quite a relatively long period of time, for the memory to yield the contents of the location of that address. And maybe it's, it's 250 nanoseconds or 500 nanoseconds, right? And then at that point, the CPU can ask for the data in this register to be transferred onto the data bus. All right? So that the second line here is actually connected to the address register. The CPU unit will actually put a memory address into this register. So logically, to read from memory, you need an address and somewhere to put the data that comes out. Put it into the MBR. Here's the MBR. Right, so what we're looking at now, because I'm separating our system that we've looked at in the previous week or so, by some new hardware components. I've got a controller here, and it's called the Cache Interface Controller, the CIC. And I've got the cache memory itself, which, as we've seen, is very high speed. And I'm going to spend the next 5 minutes just discussing the operation of this system, because it's worthwhile knowing how it works. So the CIC
is actually going to control and work on behalf of the CPU. What do I mean by that? Well, it can intercept a read signal, and if it gets a read signal, what it's going to do is to relay the read command or the read instruction to main memory. And this is after the CPU has actually put an address into this register, and it's going to wait. But at the same time, the kick is actually going to send, I think it's a check command, a check signal to cache. It's asking cache memory as to whether inside cache there's anything corresponding to a particular address, and does it have data corresponding to that address. Now, the beauty of a cache system is it's going to operate very, very quickly. And you remember, cache memories are going to be fairly expensive, but fairly low capacity. What a cache is actually going to do within a couple of nanoseconds is to send a signal back to the cache interface controller saying either hit or miss. And hit means, yes, I do have a copy of something corresponding to the address that's currently in the MAR, and I've actually got the data. So in that case, if you get a hit, you're going to abort the main memory read instruction, and you're going to ask cache, as a side effect of doing a check, you're going to output the data that it contains that was originally in main memory. It's got a copy of it, and that can be transferred back to the CPU very, very, very quickly indeed. And we're talking about something like 250 nanoseconds versus, I don't know, 10, 20 nanoseconds. Do all that. So there's a saving in time. But we've just got to consider the case where, okay, the CPU asks the system, which is being controlled, it's going to be managed by the kick, to do a read. And this time, go ahead and attempt to read memory at the same time that you're checking to see whether cache knows anything about this address. And if cache doesn't have a copy of the location indicated by this address, what it's going to do after the memory does its read, because it's going to be allowed to finish the operation of reading from memory, it's going to make a copy of this address and the data corresponding to that address in main memory. So in the case of a miss, you're actually going to put something into cache. And the idea here is, now listen very carefully, the idea behind all this is that locality says in the very near future, the CPU will again want to read the same thing from memory as it has just read. And again, what happens is that the kick will ask the cache to be checked, and this time it'll return a hit, so you don't have to go through the whole process of reading from memory again. It's a waste of time. You've got a copy of data in cache, and it's available to the CPU by cache putting the data or the instruction or whatever it is into the data buffer. Sorry, the data bus. So, just a little bit of explanation here. And the problem will be to understand the implementation of the kick, and I've given you, a fair copy of what I've just told you, how it operates. So, and a bit more. And these are some of the things I want you to understand. The kick can abort a main memory operation because it's it's unusual, but all it means, if it does abort a main memory read, is that it's got a copy of the data or the instruction it needs in fast cache. Cache takes an order of magnitude less time to perform read or write operations. It's very, very quick. Cache can be interrogated as to whether it contains a copy of the main memory location A for some address A, and the result is known with a miss or a hit within a split second of nanoseconds, in terms of nanoseconds. And we can read data from the cache and write data to it. Right? So we've seen that the need to write data, whenever we get a cache miss, we put the data that's being read from main memory into cache. So cache is quite beautiful in the sense that it's not like ordinary random access memory, and you can't address it directly. And cache has similarities to human memory in the sense that what goes in is not an address. What the input is data, and the cache is going to do its operations in parallel. It's going to search for a particular address in parallel. So if you've got something like 4096 cache memory cells, it's going to search each one in parallel for a particular address. Right. Cache interrogates each cell in a bit and word parallel fashion, and I'll talk to you again about the structure of cache later on. And the only job of a cache interface controller is to supervise all the local operations. So what the kick does is to spring into action if the CPU wants to do a memory read or a memory write, which we haven't thought about. I think IBM research from, I guess it's at least 15 years ago, resulted in the fact that generally a computer system does as five as many reads as writes. So all being well, the use of cache, the effective use of cache, is going to result in a big speed up of memory, and hence the running of a program. So I'm going to skip the next few pages until we'll return to some of this a bit later on. So we're looking for part 3, where I'm actually going to prove to you that there's some advantage in using cache. So I'm going to first of all, so it's not last week, it's about half an hour ago, I mentioned the idea of finding a word in cache, a hit, or not finding it, a miss. The idea of a hit ratio is now going to be defined, and there's conclusive evidence from research done by IBM that a hit ratio is of 0.7 is typical, even with using a small cache. And this means, in effect, that for 70% of operating time, the item that the CPU needs, i.e. a particular item of data or particular instruction, will be found in high-speed cache. So here we go. Hit ratio is the number of hits divided by the total number of accesses of memory. So if you've got a hit ratio of 70, it simply means that 7 out of 10 times, or 70 out of 100 times, you're going to get a hit when you access, you're checking cache for the presence of a particular address. And in general, the hit ratio is quite close to 100%. If the system's designed well and the programs executed all have locality properties. But the fact of the matter is that most programs do have locality properties in the way in which I've described earlier. So second definition is a miss ratio, and it's defined as the 1 minus the hit ratio. So if I've got a hit ratio of 0.9, the miss ratio is going to be 0.1. And miss rate is the probability of not finding what you need, what you want, what you're looking for in cache. So I'm going to define the average time to access data or instructions from memory, from all the memory that you've got over a given observation period. And it's this. It's the miss rate multiplied by the time it takes to access main memory plus the hit rate times the time it takes to access cache. So if you've got a hit rate of 0.9 and the access time of main memory is 200 nanoseconds, just for the sake of argument, and the access time, the read-write time it takes cache to finish its operation is 50 nanoseconds, we obtain the average time to access data in your computer system to be 0.9 times 50 plus 0.1 times 200. And I think I'm right in saying that comes to 45 plus 20, and that's 65 nanoseconds. So the average time it takes to get something from memory is 65 nanoseconds. And please note, without cache, it's going to take every memory access 200 nanoseconds. Without cache, 200 nanoseconds. That's how long it takes to access main memory. We've got an average, a new average of 65 nanoseconds, which is 135 nanoseconds less. So that's pretty good. It's as though memory is all memory is accessible close to the time it takes to access the fastest memory in the system. And here's my conclusion. Hence, we have succeeded in collapsing the classical memory hierarchy in exactly the sense that we can have lots of slow memory in the system, providing we've got cache, and then we get an average access time not close to the slowest memory, but close to the fastest memory. So more examples of locality. I don't know if, it holds for Windows 10. If you type a Unix command, for example, cd to this folder, and later on, shortly afterwards, I want to repeat that operation at a later stage. I simply press the arrow key and the command reappears. So all the commands I type in have been cached because it's recognized, for example, if you type in a particular URL, that there's a high probability that in the near future you're going to type in the same URL. So your computer system maintains a copy of everything you've typed in over the recent period that you've been using the computer. And here's another example. Having money in your pocket is a form of caching, or having money in your purse is a form of caching. If you put money in your pocket, there's a probability that your pocket will be accessed again and again in the near future. The cash in your pocket has been taken from your bank account, which is fairly time consuming to access. You have to go into the perhaps go into the bank and ask for £10 cash, or go to the cash machine and get £10 up. It takes time. Keep the cash in your pocket, and so on. So I'd like you. That finishes this part of the of topic 3. I'd like you to think of more examples of the principle of locality. And let me just finish on this note. Think about the position of your left foot right now. In the next few milliseconds, there's a very, very high probability that your foot will be in the same position. Oh, and it might be wrong, because you might have just moved. You might be standing on your feet and walking as you listen to this. I mean, it's entirely possible, after all, to listen to my lectures using a smartphone. You can access these presentations quite well and quite effectively using an iPhone, for example. On the other hand, you could actually say, well, think about the expression on your face. It's highly unlikely to change in the next few milliseconds, or perhaps the next few seconds. Locality says there's a high probability that it won't. Anyway, I'll leave you with that thought, and thank you for listening. Goodbye.